Hi guys, and welcome to another session. In this week we are going to be talking about model evaluation. So if you managed to get through last week, then congratulations, you just created your first data science machine learning algorithm. But in this session we're going to build on what we already know and take things a step further. So one of the things that you will commonly want to do when you are designing data science algorithms is understand how well your algorithm is performing. This is the idea of evaluation. You want to be able to evaluate the performance of your algorithm. So we know that we're in a situation where we've gone out and gathered a bunch of labeled data. So in our example, we were talking about cats and dogs. So we had a load of measurements of the animal weight and the animal tail length, and then we had an associated label, so whether it was a cat or a dog. So that's our kind of data. And then we have this sort of new set that comes in where we don't know if it's a cat or a dog, but we want to make a prediction. We've got its weight, we've got its tail length, and we want to find out whether it is a cat or a dog. But once we've made this guess, who's to say whether we've done well or badly? We don't actually know. So we would like to be able to come up with techniques for assessing how well our algorithm is performing before we go live. Like say you were running a company and you wanted to kind of predict, I don't know, what type of ice cream that a customer would like based on their, I don't know, preferences for something else. You'd want to know how accurate your prediction was before you deployed it live. It's quite important that you have a sense of is this algorithm any good? Is it going to get 100% right? Is it going to get nothing right? How do we know? So that's what we're talking about this week. So how do we measure how well our algorithm is doing? Like say we knew what the true label was, but we asked it to make a prediction anyway. How would we know how well it was doing? Well, a kind of quite a simple metric is just the accuracy. So this is basically just what percentage of our guesses did we get right. So you could think of it, like if you're taking a kind of test at school, you would, and you got sort of 30 out of 40, then your accuracy would be 30 divided by 40, or 75%, or 0.75. And with our algorithm, we're basically giving it a test. We're saying, is this a cat or a dog? And it's going to make some kind of guess, and then based on how many it gets right, we can work out the algorithm's accuracy. If we knew what the true labels were, then we could work out the accuracy. So that's what we're going to be talking about this week. And for this lesson, you're going to need a new package, and this one is called Scikit-Learn. Now, Scikit-Learn is really widely used. It's a great Python package for doing machine learning and data science. It's kind of one of the four sort of standard packages that every data scientist will use at one time or another. And those four packages are NumPy and Matplotlib, which we've already looked into. Another one called Pandas, which we probably will do at some point, and this one called Scikit-Learn. So you're going to need to install Scikit-Learn, and while you're there, you might as well install Pandas and NumPy and Matplotlib if you haven't already. So you just go to your command line. So if you're on Windows, you do that by typing CMD into your Windows Start menu, and then clicking on the command prompt program. And then if you just type into your command prompt pip install NumPy, Matplotlib, Pandas, Scikit-Learn, and note that there's a little dash there between the Scikit-Learn, so you make sure you get that exactly how it is. And if you run that, you should be able to install all of those packages. And if you've already got NumPy and Matplotlib, it doesn't matter. That won't cause a problem. It'll just say you've already got them installed. So don't worry about that. And then once you've done that, if you head on over to a Jupyter notebook like this one and type import sklearn, then if you have no errors, then everything worked fine, and you have managed to install Scikit-Learn. And if you do have any problems with installing, don't hesitate to just contact me, reach out, and I'll make sure that you can get that done. Okay, so last week, what did we do? Well, we were looking at this machine learning algorithm called 5 nearest neighbors. And just as a reminder, the way that this algorithm worked was we gather all of our data and we plot it on a graph by sort of it's x, putting the point. So for each example that we have, we've got a weight and we've got a tail length. And then each example will basically plot as a point on a graph. And it's sort of x distance will be its weight, and its y height will be its tail length. Or the other way around, it doesn't really matter. So that's the first thing we do. We take all of our example points that we know, whether it's a dog or a cat, and we plot them on this graph. And then you could, for example, color these points based on whether they're a dog or a cat. So you could put all the cats in one color, all the dogs in another color. And then what we do is we, for the new point that we want to guess, so this has a certain weight and a certain tail length, but we don't know if it's a dog or a cat. So we plot this new point on the graph, and then we measure the distance between this new point and every single other point on the graph. And then we take the 5 closest points and we say, are there more dogs or are there more cats? If there's more dogs, then we guess that this new point is a dog. If there's more cats, then we guess that the new point is a cat. So we're just going to do some imports here. So these are just the regular imports that we like to do for Jupyter Notebooks. So we're just importing NumPy, Matplotlib, and we're going to set some print options. And then here we're going to run this graph, which just gives us a reminder of what we did last week. So in this example, we've plotted all of our points on the graph. So you can see all the cats are in orange and all the dogs are in blue. And then this new point here, which we don't know if it's a dog or a cat, we plot, and we basically have drawn the line to the 5 nearest points. And you can see here that 4 of these points are dogs and 1 is a cat. So we've colored this new point blue to indicate that we're going to predict that it's a dog. But we can move this around and see what happens. So you'll see at a certain point, once we get close to the cats, it's going to change, right? So now we've actually got more connections to cats, so we're predicting that this new point is a cat. So that's the idea. So in order to kind of begin talking about the accuracy of an algorithm, we need to talk about 2 important concepts, and they are training data and test data. So we've received all of our data. So we've got this big block of data where we've got all these measurements, we've got all the weights, we've got all the tail lengths, we've got all the labels indicating whether it's a dog or a cat. What we're going to do is split this data into 2 distinct groups. And one of these groups is going to be called the training data, and one of these groups is going to be called the test data. So the training data is going to be a bunch of examples. So it's going to be a load of measurements along with their labels, and the test data will be the same. Except we are generally going to split them in a ratio that means we have more training data than test data. So a usual kind of thing would be 70% training data and 30% test data, or 80% training data and 20% test data, something like that. And then basically what we're going to do is we're only going to use the training data to make predictions. So we're going to basically use the training data to predict what the true label is for all of our test data, but we actually know what the true label is because that was part of our original data set. But we're going to use our training data to predict that anyway. And then we're going to compare the true labels with our predicted labels on the test set, and then that's going to give us an idea of our accuracy. So the first little exercise here is just to import some data. Now, this is in a slightly different form from last time. We're basically going to be using NumPy arrays for this data. In particular, we're going to be using a 2D NumPy array for our animal measurements, and a 1D, or just a normal NumPy array, for our labels. So our measurements are basically going to be this kind of rectangle of numbers where the columns represent the different measurements. So this column is going to be all of the weight measurements, and this column is going to be all of the height, tail length measurements. So this is, for example, is an animal with a weight of 6.6 kilograms and a tail length of 43 centimeters. And then associated with that is an array of labels. So the length of this array should be the same as the kind of height of this array, because each one of these corresponds with the same animal. So for example, this first animal here with a weight of 6.6 and a tail length of 43 centimeters is a cat. It's 0. So remember, 0 represents a cat and 1 represents a dog in our in the way that we've built this problem. So this is basically a way of having all of our data in one place. So we're going to just import this data. So I've kind of pre-written this data. It's coming from another place. So the first thing here is just to kind of, if you read these exercises, just to print out these variables and have a look at their shape, importantly. What that means is basically, so if we have an NumPy array, let's say np.array of 1, 2, 3, 4. So that's an array that looks like that. It's a square array. It's a 2D array. And if we go dot shape, it's going to say it's 2 by 2. So, but we could add, for example, another row in here. We could say 5, 6. And let's look at that array. So this is a 2D array. And you can see now that it's a kind of rectangle. And if we do the dot shape there, it's going to say 3, 2, which means it's got a height of 3 and a length of 2. So if you just sort of look at these things, x and y, and these are arrays as well. So this array is a 2D array and this is a 1D array. And you can look at the shape of these arrays by doing the dot shape thing. And just print those things out there and get to grips with that piece of data. Okay, so part B of this exercise, once you've done that, is can you tell how many dogs and cats there are respectively in this training set? And the hint here is what happens if you decide to sum up this Y array? What does that tell you? Okay, cool. So we're now going to use a Scikit-Learn function to do this, to split our data into a training set and a test set. So remember back here we were talking about a training set and a test set and how it's important. Well, basically Scikit-Learn has a kind of built-in function that allows us to do that quite easily. And that function is called train test split. So we can do from basically Scikit-Learn import train test split. And we're going to use this function, and what we're going to pass into this function is x, so that's all of our measurements, y, so that's all of our labels, and we're going to say the test size is 0.2, so that means we're going to assign 20% of our data to be in the test set and 80% to be in the training set. And random state equals 1 here just means basically because this is a random process, the algorithm, this train test split here is going to randomly split our data and put a random load of them over to be training data and a random load to be test data. And by passing random state equals 1, that just ensures that if we sort of do this again, we're going to get the same split if we pass the same random state in here. So for example, if I did random state equals 2, then we'd actually get a different split. But if we put random state equals 1, we're guaranteed to get the same split every time, which is just useful when you want to reproduce something. So we can, let's just run that one there, and then we can run this one here. Oh yes, and then the other thing I was going to mention is this train test split thing here is returning 4 things. It's going to return 4 things. It's going to return this x train. So this is going to be the measurements for the training data. It's going to return x test. These are going to be the measurements for the test data. It's going to return y train, which is going to be the labels for the training data, and y test, which is going to be the labels for the test data. And it returns 4 things. This function actually returns 4 things. And we can see that by, if we sort of go into a new cell here, paste that in and do question mark, we can look down and at some information about this function, and you should be able to see, yeah, it's returning a list, and the list is basically going to be a list with 4 items in it, and we're basically deciding to split those 4 items into this here: x train, x test, y train, and y test. We can kind of assign each one of these things inside the list directly into a variable, which is something nice that you can do in Python. That's called unpacking. Okay, so try printing. Print. Oh my gosh, printing those out and take a look at the shape. So take a look at xtrain, xtest, ytrain, and ytest. Print those arrays out and take a look at their shape and see what you can notice about them for exercise 2. So the next thing that we're going to do is we are going to use Scikit-Learn to make a nearest neighbours classifier. So what we're doing here is we're doing from scikit-learn.neighbours import the kneighbours classifier. And then we're going to say the classifier is, we're assigning a new object here, and this object is the nearest neighbours classifier with 5 neighbours. Okay, so n neighbours equals 5. And then what we're going to do is we're going to call classifier.fit xtrain, ytrain. And what that means is we're basically passing in our training data into this algorithm and saying, this is the data that you have available to make predictions. So the classifier is going to kind of ingest this training data, and then next, if you ask the classifier to predict on something, it's going to use all of these points to make that prediction, i.e. these are the points that are going to be sort of plotted on that graph, and then for a new point, it's going to use these training points, it's going to find the distance between all of these training points and use that to make the prediction. So we can run this cell here, and you can see we get something out here, which we don't need to worry about too much. So there's just some more information about that there. And then once we've made our classifier and we've sort of ingested that training data, we can use it to make a prediction. So in this line, we're saying y predict is the classifier dot predict on xtest. So xtest is basically a number of different examples, and we're basically asking it to make a prediction for each one of these examples. So for every single one of these examples, make a prediction and then store that in an array called y predict. So we're doing this on the test data. So we're trying to predict what the true labels are on our test data. So we can run that there. So exercise 3, just try printing out the variable ypred for ypredict, and what do you notice about it? Also print out the variable ytest and see if they look similar. Hopefully they should look similar. If our classifier is doing a good job, we should get quite a few of these right. And for the next part, just try to print out ypred equals ytest. Now what that is going to do is it's going to give you a new array where it's going to basically compare the values at each of the elements of these two arrays, and if they're equal, then the corresponding value in the new array is going to be true, and if they're not equal, then the corresponding value in the new array will be false. So we're basically going to get an array of true or falses. So try printing that out and see if that makes sense. Finally, type ypred equals ytest.sum and see what you get. So now, interestingly, if you have an array of true or falses, so we call them booleans in programming, if you have an array of booleans, in NumPy, if you try and sum that array, which, that might not make sense, how do you add trues and falses? What NumPy will do is it will basically assume that all of the trues are 1 and all of the falses are 0. So by doing ypred equals ytest, now we're putting this in brackets because this is one whole thing. It's an array where these two things are compared. And then we do .sum, then that's going to basically add up. It's going to tell us how many of those values were true. Okay, so one thing we can do here is import another Scikit-Learn function called accuracy score. Now what that's going to do is basically we can pass in to this function our test. So this is the sort of true labels for our test data and our prediction. And then basically this accuracy score function is just going to tell us how many we got right. So we're basically just storing that in a value called accuracy, and then we're just printing out this accuracy here. And we're multiplying it by 100 to get a percentage. Great, so the accuracy of our predictor was 93.75%, which is not too bad. But also we could have probably just worked this accuracy thing out ourselves. And that's what we're going to do here. So as before in this kind of example here, what we're doing is we're saying the number that we got correct is basically this array here. So let's just take a look at this now. I think it's probably worth just having a look at what ytest equals ypred is. So you can see that it is an array of booleans. So, ytest is just a bunch of zeros and ones, and ypred is just a bunch of zeros and ones as well. And when we say ypred equals ytest, it's a bunch of trues or falses telling us whether those two things are equal at that corresponding element. You can see that most of them are. We've got a lot of trues here, which is good. That means our classifier is getting a lot of these right. But there's also a few falses here. There's some wrong ones here and there. So if we add these up, we do .sum. That's going to basically add. It's going to assume that all of the trues are ones and all of the falses are zeros. So we are going to basically find out how many of these we got right. And the answer is 150. So that's what we're doing here. We're saying the number correct is ytest equals ypred.sum. We could also do mp.sum here. We've got some options. It'll give us the same thing, or indeed just the Python function sum. These will all give us the same things. It's just a matter of choice. So that's what we're doing here. The number correct is ytest equals ypred.sum. And then we're saying that the total number is going to be the entire length of the ytest array. So this is the entire length of all of our labels. So that's the number of total guesses that we made. And we're just going to say that the accuracy is the number correct divided by the total number. And if we want to convert that to a percentage, we can multiply that by 100. There we go, 93.75%. So that's the same. So one kind of further way that we might seek to analyze our data is by sort of not only looking at the accuracy alone, but kind of looking at it, kind of breaking it down in a bit more detail. What do I mean by that? Well, if you think about it, when we make a prediction such as this, there's basically 4 possible things that can happen. Either we can predict it's a dog, and indeed it is a dog. We can predict it's a cat and get that right. Yes, it's a cat. We could also predict that it's a cat, but actually it was a dog. And we could also predict that it was a dog, but actually it was a cat. So there's basically 4 possible outcomes. And the way that you can kind of basically think about this is by using something called a confusion matrix. Now, a confusion matrix, it sounds complicated, but actually basically it's just these 4 things right here. So the confusion matrix tells us, out of all our guesses, how many did we correctly guess were a dog, how many did we correctly guess were a cat, how many did we incorrectly guess was a cat, and how many did we incorrectly guess was a dog. So we can use, again, a Scikit-Learn function here. So we're going to import the confusion matrix function. And then in this confusion matrix function, we're just going to pass in our true labels and our predicted labels. And we're going to assign that to a variable called conf matrix, and we're going to print that out. So you can see here that what we get is a 2D NumPy array, a 2x2 2D NumPy array. And the meaning of each one of these numbers is, so up at the top left is basically where we guess it was a cat and it was indeed a cat. So I guess it was a 0 and it was a 0. And that's also known as a true negative. Over here, we guessed it was a dog, but it was actually a cat. So that is what's known as a false positive. Down here, we guessed it was a dog and it was indeed a dog. So that's a true positive. And over here, we guessed it was a cat, but in actual fact, it was a dog, and that's called a false negative. You might have heard some of these terms, true positive and this kind of thing before. One of the contexts that you often hear about it is in medical trials and medical settings. So often, for example, if someone is being tested for some disease, so what will happen is you'll get a test and it will say you either have the disease or you don't have the disease. And it will either be right or wrong. So a true negative would mean you don't have the disease and it tells you you don't have the disease. A true positive would be it tells you you have the disease and indeed you do have the disease. But a false positive would mean the test tells you that you have a disease but actually you don't have the disease. And a false negative would mean it tells you that you don't have a disease, but you actually do have a disease. So that's kind of one of the way sort of places that you might hear about or you might hear these terms. Okay, so one other thing that we can do is actually just plot this confusion matrix, as it's known, in a slightly nicer way. And again, Scikit-Learn has some functionality for this. So we can import this thing called confusion matrix display. And then what we pass to this is the confusion matrix that we just defined up here. And then the display label, so we're basically telling it, well, what is a 0 and what is a 1. And then we're asking it to plot CMap equals plt.cm.blues. That means just kind of what color should the plot be. So if we run that, we're going to get this visualization here, which kind of makes it a bit more clear. So down here we have the predicted label, over here we have the true label. So you can see 52 times our classifier correctly predicted a cat, 98 times our classifier correctly predicted a dog, 8 times it incorrectly predicted that it was a cat, and twice it incorrectly predicted that it was a dog. Okay, so the very last thing that we're going to talk about is this idea of tuning hyperparameters. So you might have already noticed that originally I was referring to this algorithm as the 5 nearest neighbors algorithm. But actually the more general name for this algorithm, which you might have seen already when we imported it from Scikit-Learn, is the k nearest neighbors algorithm. And that's because we don't actually have to choose the 5 nearest neighbors when we make our prediction. You could choose the 1 nearest or the 2 nearest or the 3 nearest or whatever you want, and make your prediction based off of that. And that's the idea of the k. So the k here means how many neighbors are we actually considering. And it's what's known in machine learning as a hyperparameter. So this is basically something that we have to choose. We can vary it in our model. And it's basically just a decision that you will have to make as a data scientist. But how do you know that you're making the best decision? How do you know that you're making the hyperparameter decision that leads to the highest accuracy? Well, that's where this kind of test data and training data comes in really handy. So what we can do, for example, is go through each one. So we could basically retrain the algorithm a bunch of times with different hyperparameters and see how the accuracy changes. And then we're going to basically want to choose the one that has the best accuracy. So take a look at this little code down here. So what we're doing is a loop. So we're doing a for loop. So we're saying for k in this thing here, in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically we're going to do a loop. And on each iteration of the loop, this value of k will be updated. So first it'll be 1, then it'll be 2, then it'll be 3. And then for each one of those loops, we're going to say we're going to make a new classifier. So we're going to say the classifier equals k nearest neighbors classifier. And then we're going to say that the number of neighbors that we want to consider is k. So this is our hyperparameter. This is what we're changing on each iteration of the loop. And then we're going to say this classifier, we want to fit it on our train data and our X train and our Y train. So our measurements and our labels. And then we're going to say that our prediction, ypred, is classifier.predict on the test data, so X test. And then we're going to calculate the accuracy by doing accuracy equals accuracy score on our prediction and our test data. And then we're going to print out basically the accuracy corresponding with this value of k. So you can see here when k is 1, we get an accuracy of 94.4. When k is 2, we get an accuracy of 93.8, and so on and so on and so on. So exercise 4 would just be which value of k would you choose and why? So the very last thing that we're going to talk about is something called cross-validation. Now, one thing that you might realize here is that there's still some randomness. So when we make our decision to split some of the data off into training data and some of the data off into test data, that was random, right? We made a random choice and we're basically judging the performance of our algorithm off of that random choice. But what if we'd split it in a different way? What if we'd chosen a different set of test data and a different set of training data? Maybe the predicted accuracy of our algorithm would change. So this is where the idea of cross-validation comes in. So the idea is basically this. We're going to split our data up into 5 chunks. So because we're going to split it evenly into 5 chunks, but basically it's going to be sort of 20% in each chunk. And then basically for each of these chunks, we are going to separate them. So we're going to separate one chunk away from the other 4 chunks and say that the one chunk is going to be our test data and the 4 chunks is going to be our train data. We're then going to let our algorithm predict the labels of our test data using the training data and then compare it to find the accuracy. But what we're then going to do is we're going to put that original chunk back into the data set, mix it out, and take out a different chunk, and then we're going to use this chunk that we've just taken out as our test set and the other 4 chunks as our training set. And then we're going to do the same thing. We're going to use this new training set to make a prediction on this new test set, and that will give us a new accuracy. And we're basically going to do that for all 5 chunks. So we're going to basically get 5 different guesses for the accuracy of our algorithm. And then we can just take the average of those 5. So that might give us a kind of better impression of what our true accuracy is. So that's a little bit of a strange concept. So just pause the video and sort of take your time to sort of digest that if that's not making sense immediately. So again, Scikit-Learn is helpful here in that it gives us a way of basically doing this really quickly and easily. And that's by using this function called the cross-val score. So what we're doing here is we're doing from Scikit-Learn import this thing called cross-val score. Now what cross-val score is going to do for us is it's basically going to, we can give it our classifier, we can give it our data, and then it will basically tell us the accuracy across all 5 of these chunks. So what we're doing here is a loop again. So we're doing for k in all of these numbers as before. And then on each value of k, we're going to make a new classifier. So this classifier is a k nearest neighbors classifier, and it's going to have k neighbors, k being the thing that changes. And then we're going to say that the scores is the cross-val score, and what we're passing in here is the classifier, so this, and our x data and our y data. So all of our x data and all of our y data. And so basically all of our measurements and all of our labels. And we're just saying CV equals 5 means we're going to split it into 5 chunks. I'm going to cross-validate with 5 chunks. And what it's going to do is it's going to give us these 5 accuracy scores. So it's going to tell us what the accuracy was on one chunk, what it was on another chunk, what it was on another chunk, what it was on another chunk, and another chunk. And then basically what we're so this is kind of like a NumPy array of 5 different accuracy scores. And then we're going to see our average accuracy was the scores.mean, so the mean across all of those. And again, we're going to print out our average accuracy for each value of k. So there you go. You can see we've got some new accuracy scores here. So your final exercise here is based on this new information. What value of k would you choose? Is it the same as before? Has it changed? Why? Which one's better? So yeah, have a think about that. All right, well, thanks a lot, guys. That's the end of this lesson, and I will see you next week.